Morning students, in today's lecture we will discuss problems related to pressure on curved surfaces. First problem is a hemisphere of radius A is placed with its center at a distance h below the surface of water and has its plane face vertical. We are to find the horizontal thrust on the curved surface and also the resultant thrust on it. So let us consider a hemisphere with ACBT, its plane base. This hemisphere is placed in water in such a way that this plane base ACBT, that is vertical. O is the center, which is at a depth h below the free surface. Now, to find the horizontal thrust on this curved surface, let us take x and y. These are the horizontal thrusts along two mutually perpendicular horizontal directions OA and OE. Let us find x. X is the resultant horizontal thrust along this direction OA. By definition, x is the resultant thrust on the projection of the curved surface on the plane CDE. This is perpendicular to OA, and so x will be 0 because this curved surface is symmetrical about the plane CDE. Now let us find y, which is the resultant thrust along the direction OE. By definition, this is resultant thrust on the projection of the curved surface on the plane ACBT. So we can say that it is resultant thrust on the circle ACBT. By definition of resultant thrust, this is given by density into g into depth of center of gravity below the free surface into area of the circle ACBT. Now depth of center of gravity below the free surface, that is given to be h. Density of the liquid is rho. Here the liquid is water, so we have considered the density of water to be rho. So the resultant thrust on the circle ACBT, that is given by rho into g into h into pi r square. Here r is the radius of the circle ACBT. Now it remains to find the resultant vertical thrust. We have denoted it by z, and by definition the resultant vertical thrust on the hemisphere, that will be the weight of the superincumbent liquid that fills this hemisphere. So this is given by volume into density into g. Volume of hemisphere, that is 2 by 3 pi r cube. Density we have taken as rho, so z becomes 2 by 3 pi r cube rho g. So we can find the horizontal thrust on the curved surface, and by definition it is given by square root of x square plus y square. Now because x is 0, so the horizontal thrust on the curved surface, that will be y, and the value of y we have already obtained. This is rho g pi r square h. So in this way we have obtained horizontal thrust on the curved surface. Now to find the resultant thrust. Resultant thrust is given by square root of x square plus y square plus z square. Putting the values of x, y and z here, we get the resultant thrust, which is given by 1 by 3 rho g into pi r square into square root of 9h square plus 4r square. So this gives us the resultant thrust. Now the next problem is a closed cylindrical vessel with hemispherical ends is filled with water and placed with its axis horizontal. We have to find the resultant thrust on each of the ends and also its line of action. So let us consider a closed cylindrical vessel with hemispherical ends. This vessel we have considered A, B, C, D, E, F. R is the radius of hemispherical ends. Let us take X and Y are the horizontal thrusts. X is the horizontal thrust on the curved surface of the hemispherical ends along OX, and Y we have taken the horizontal thrust on the curved surface along this line OY. Let us find them one by one. Now by definition, X, which is the horizontal thrust on the curved surface of hemispherical end along OX. This is the thrust on its projection in the plane A-F-B-D. So that will be the thrust on this circle. So by definition, this is given by rho into G into depth of center of gravity into area of the circle. Area of circle is pi r square. Depth of center of gravity is r. So this will become rho G pi r cube. Now the horizontal thrust on the curved surface along this line, that will be 0, because we can see that there is symmetry of curved surface about the plane AFDC. Now it remains to find the resultant vertical thrust. Now the vertical thrust on the curved surface, that we have denoted by Z, that is the weight of superincumbent liquid, means weight of the liquid that is contained in the hemisphere. So that will be given by volume of the hemisphere into density into G. Volume of hemisphere, that is 2 by 3 pi r cube, density is rho. So the weight of superincumbent liquid, that becomes 2 by 3 pi r cube rho G. Now because the forces X, Y, Z, these are intersecting forces, so the resultant thrust R, that is given by square root of x square plus y square plus z square. We can substitute the values of x, y and z. X is rho G into pi r cube, y is 0, z is 2 by 3 pi r cube rho G. Putting these three values here, we get the resultant thrust R, which is given by under 13 upon 3 into pi r cube rho G. Now it remains to find the line of action of the resultant. For this, let us take theta is the angle made by the resultant thrust with OX direction. So by definition, tangent theta, that is given by Z by X, putting the value of Z and X here. Value of Z is 2 by 3 pi r cube rho G and X is rho G pi r cube. So tangent theta, that becomes 2 by 3. So from here we can find the value of theta, which is given by tangent inverse 2 by 3. So this gives us the line of action for the resultant thrust. And this completes your chapter, pressure on curved surfaces.